Loud. Okay, so good afternoon, everyone. My name is Alberto Caban-Martinez. I'm an associate professor of public health sciences at the University of Miami Miller School of Medicine. It is my privilege to welcome you on behalf of our PI, Dr. Aaron Kobitz, and all the team members of the Firefighter Cancer Initiative to our first and inaugural FCI educational cancer series. This year, as we kick off year 6, now in its second month, our goal is to be able to provide regular and periodic updates on the educational topics that we're learning through the research conducted through FCI. It's important to us to make sure that there are opportunities to share in live as well as recorded the findings of the different studies that we are doing. So to kick off our inaugural series, we're gonna selected to present a topic that my graduate student, Kevin Griffin, just presented in May as part of his 2-year Master's of Science in Public Health thesis. To us, this is a really important project because it allows us to begin to develop a different approach to assessing carcinogenic exposures in our first responders. Today's session will be about 1 hour. I'll try, if you will indulge me, to get through most of the slides and present the topics. There is a chat function available to you here for this recorded session. So if you wouldn't mind just popping in your questions into that chat function, and then towards the end, I'll start entertaining those questions through a Q&A component. We'll try to do a hard stop at 1 o'clock. I have 53 medical students I have to go teach at 1 p.m. So it'll be a quick stop. But if I don't get to your question during today's session, please do feel free to email myself or my graduate student, Kevin Griffin. We'd be more than happy to share with you anything from the study. So I'm calling this seminar today, Toenails as a Biomarker of Long-Term Exposure to Heavy Metals in Firefighters. This was a research project that was funded by the Sylvester Comprehensive Cancer Center through a research grant with my colleague, Dr. Shanta Dar, and our lab. It was sort of like an integrated research project of trying to put together basic science and applied sciences in the field. And we called this project the HEAT Firefighter Study. And so HEAT stands for Heat Metal Exposure Assessment using toenails. So hopefully we won't gross you out and you're not having lunch in this next hour, but find the information useful that we've been learning in this project. So I want to begin by defining the problem of why we're looking at heavy metals in firefighters as a source of, as a catalyst of cancer. So this is a slide I like to use often that reminds us that IARC, the International Association for Research on Cancer, they are a sub-agency of the World Health Organization, and their primary function is to be able to characterize and put together literature based on evidence on what is carcinogenic and not carcinogenic. And so one of the things that we are learning is that through this monograph, particularly one that was published in 2010, is that firefighters are at an increased risk for certain types of cancers. So which cancers did this monograph identify? So when they took the literature together, and this is including domestic, meaning United States, plus internationally, all of our firefighters around the world, the evidence suggests at the time, this is now 10 years old, that prostate cancer, testicular cancer, and non-Hodgkin's lymphoma and thyroid cancers are elevated among people that work as a firefighter compared to the general population. In fact, the title of being a firefighter was classified as what we call a group 2B carcinogen, right? So it's kind of weird to label a title as carcinogenic. You know, you normally label exposure to a chemical substance, but in this case, the evidence was sufficient to convince the subject matter experts that sat on this committee and monograph that the title of being a firefighter in and of itself is possibly carcinogenic to humans. It was in the same monograph where they labeled shift work and painters as also susceptible to cancer. So you can imagine our firefighters, not only because of their exposures, but also because of the organization of their work, right? So they also engage in shift work. So what are some of the risk factors taken together, like shift work and exposures, that could be increasing that risk? And so why is there a risk for cancer? So I'm sure our firefighter partners on the Zoom call today know that you are exposed to many hazardous physical, chemical, and mental exposures when you're out on the field, whether it's an EMS call or a fire rescue call. You are exposed to different types of hazards than the general population. When we look at fire response calls and fire suppression activities, the plume of smoke that you encounter is unfortunately high with different types of carcinogens. We've been able to document in the scientific literature that you're exposed to items such as polycyclic aromatic hydrocarbons. These are products of combustion. So when the furniture is burning, those materials give off multiple different particles, both free-flowing and bound. Some of these are aromatic hydrocarbons, a big family of different hydrocarbons that some have been known to be carcinogenic to humans. This also includes VOCs, organic compounds, and different particulate matter. So exposure to these carcinogens has been supported by analysis of firefighter blood and urine profiles. So during specific studies, researchers have collected blood and urine and have been able to found the metabolites of these carcinogenic compounds inside the urine and the blood profile. So that already suggests to us that you're being exposed to it as it enters the body through these biomarkers. So one potential exposure of interest for us is exposure to heavy metals, which is also present in the plume of smoke. But what is a heavy metal exactly, and why do we care about it as a carcinogenic exposure to firefighters? Well, we consider metallic elements that have really high densities when you compare it to water to be considered a heavy metal. Some of these can be very toxic or even poisonous to a human in very low concentrations. So ideally, in the human body, you have no levels of the toxic heavy metals in your blood. Some of the heavy metals that we find are copper, selenium, and zinc. Those are actually really important to the human body and are considered essential heavy metals. So you're like, well, wait, why, if you're saying heavy metals are bad, why would these be essential? So not all heavy metals are bad. Some are bad and some are actually really useful and have critical role functions in protein synthesis and metabolic function within the human body. So copper, selenium, and zinc are actually good for the human body, but other metals such as cadmium, lead, and mercury really don't have any biological function in the human body. So they really shouldn't be there at all. In fact, some are known to potentially catalyze cancer. Where do we find these heavy metals? So in the general community, not just firefighters, heavy metals are in many different places. So they're in outdoor dust and plume. Think about a construction worker that's at a very dusty work site with a plume of dust and particulate aerosolized in the air. They're exposed to that plume both dermally and through inhalation that can potentially be exposing them to heavy metals. If you've ever sat on an expressway or on the road in heavy traffic, you know that the air quality is not good. Through that plume of smoke from the vehicles, we are also exposed to different heavy metals. In the indoor environment at home, we are also exposed to different heavy metals through cooking, through painting, through smoking, through the different coverings that are on our furnitures, through the ages of the building, right? The construction is very important. If you're in the Northeast versus the South of the United States versus the West Coast. And also the floor level, if you're in a residential building where you're located, you might have different exposures to heavy metals. On the right, you see a plume of smoke of a structural fire. This is what our firefighters combat each and every day as they try to put out these different types of structural fires. These fires emit these heavy metals into the air and aerosolize them. So we think about the different point sources of heavy metal exposures to our firefighters, which primarily come through fire suppression. They may also have exposures that land on their gear, right? So the boots and the turnout jackets, the hoses, their safety equipment may be contaminated with some of the heavy metals, and then potentially the fire station through the diesel exhaust of the trucks, as well as what they bring back into the fire station from fire suppression responses. So what are some of the cancer risks of heavy metal exposure? So let's talk about arsenic as one of the bad heavy metals. So research has suggested that arsenic development is implicated to give cancer in the lung, the bladder, and the skin. Also, chronic low-level dose exposure to arsenic has been associated with the development of non-Hodgkin's lymphoma, and this is both in animal and human models. Cadmium, which is also a product of combustion, we see it in plumes of smoke as well as cigarettes, right? So primary or secondary smoke also releases cadmium into the air. It's been associated with the development of prostate, testicular, and thyroid cancer. And also lead, a very heavy metal, associated with the development of renal cancer and decreased thyroid function. so impacting the physiology of thyroid, TSH, T3, and T4. So you can see that heavy metals do play a role in the development of cancers, potentially increasing the risk for our firefighters. So this raises a curiosity in our scientific mind about whether or not what types and how much of these metals firefighters are exposed to. So there's many different ways that we can assess heavy metals. From a clinical perspective, the most common and frequent way to assess for heavy metal exposure or toxicity is through a blood sample. So if you've ever been to a 5-alarm fire or a really bad, nasty fire, you may be asked to do a physical exam with a physician in an emergency room or with a primary care immediately after that fire, particularly if there are symptoms that you're feeling afterwards. And part of the assessment will include a blood draw, where we can do a rapid blood toxicology panel of heavy metals to see if you're exposed to any heavy concentrations free-flowing in your blood. There's also other mediums of how you can measure heavy metals. So you can take a saliva sample and quantify what is in the saliva of an individual. Remember, saliva is produced through different glands in the face. And so if you have heavy metals circulating in your body, it will be concentrated or found present in the saliva sample. You can also select and find metals through the hair. So this is an interesting way because hair is a protein, and as the hair is built through the pore, you can have metal deposition within the keratin layers of the hair, or you can have metal on the surface of the hair. So this can be sort of it's still a biomarker that's under development because it's very difficult to tease out how much of heavy metal exposure you really have based on what's on the surface of the hair that you can just slough off versus what's actually impregnated within the protein matrix of the hair. Another way to assess heavy metal exposure is through urine. You can ask an individual to provide you with a urine sample, and you can actually count out the metal types and concentrations that are available in urine. All of these will tell you what type of heavy metal is already absorbed and is in the body and is circulating. One of our particular interests is, can we use nails as a biomarker of heavy metal exposure? Now, this is not rocket science. Actually, the use of toenails has been studied on other smaller populations, for example, within children or in general populations, as another measure of long-term exposure. There's some really good strengths, but there are some limitations to using nails as a biomarker. So nails, in terms of a strength, can be incorporates trace elements of heavy metals in proportion to their intake or exposure. So what that means is that depending on what the person has been exposed to, if today I threw a plume of smoke on you and it has certain types of heavy metals present, your body will internalize it, metabolize it, and then as the nail is growing, will deposit those heavy metals into the nail. So the proportion of that plume that you're exposed to at this given time will eventually show up in your toenail as a manifestation. So toenail clippings represent sort of a long-term exposure. If you can get a really good juicy hangnail, that hangnail can give you a really good timeline, say anywhere between 6 months to a year of your previous exposure to heavy metals. Toenails are also very easy to collect and store. It's very non-invasive. The next time, a firefighter goes to cut their nails, you ask him, can you please just, those shavings, if you can collect them and put them in an envelope for us. So there's a lot of strengths with using that as opposed to having to do, regular blood draws or collect a lot of urine samples in order to monitor heavy metal exposures. But there are limitations to it. So using toenails to look for aluminum, magnesium, copper, and zinc may not be, has not been well established. There's still a lot of scientists around the world that are trying to validate the process of using certain technology to be able to detect these metals. Also, the metals can be cross-contaminated due to nail polish or even the same cutters that you use to cut the nails. So for example, for individuals that use nail polish or paint their toenails, that polish can potentially add different metals, right, from the composition of the nail paint that is used, or the same cutter. If you're using a very old cutter, the chippings of the cutter may introduce artifact of metal into the nail at the time of cutting. Another potential limitation, it has the small nail mass samples, right? So if you cut the nails and they don't have a lot of nails of, nail shavings, then you may not have an accurate representation of that sample. So there are some really positive strengths and some limitations to consider as I present this information. So I want to just give you an overview of nail anatomy and physiology really quickly so you have an understanding of why we think that this is a really neat and useful way of studying long-term exposure of heavy metals within our firefighters. So I'm going to start off on the left just to show you some really quick anatomy of nails. So we're looking here at a finger, but there's not too much difference between the anatomy and physiology of nails between the toes and the fingers. So you can see on the top left, the anatomy of an index finger. What I want to point out to you is the lanule and the cuticle portion of the nail. So nails grow from that edge of the finger, and they grow out distally to where it's labeled free edge of the nail. So when I'm talking about shavings of a nail, I'm talking about that white part that's labeled free edge of the nail that an individual cuts off every time they cut their nails periodically. Those nails actually contain the heavy metal. So how do they contain the heavy metal? So take a look at the right. You can see an illustration here where we look at keratin, which is a protein that makes up the different layers of the nail, and interspersed you see glycated keratin that's there. So as, and I think I have an annotation pointer, so I'm going to use annotations. So as the nail is produced here on the finger, the blood supply that goes to feed the lanule, where the keratin layers are produced, is depositing blood supply rich in nutrients to the nail bed to create the keratin. So you can imagine that if you have heavy metals circulating in your blood as they here to feed the nail, anything that's circulating in there that's a heavy metal will get deposited into these keratin layers. So as the slow growth of the nail advances distally to the end, when you shave those clippings, you will get a certain timeline of exposure to those nails. So if you're thinking, well, how long it is, it's been estimated, a study that was published in 2010, looking at the growth rate of human fingernails. And one of the things that we've learned is that the average fingernail growth rate is faster at the fingers than it is at the toenails. And the difference is that the fingers grow about 3.47 millimeters per month as compared to the toenails that give you, that grow about 1.62 millimeters per month. So the toenails actually grow a little bit slower, which gives you a better, more long-term timeline of exposure to those metals. Okay. Let me just stop my annotation. Okay, so what is the study objective? Now that we have this background information, and I hopefully motivated you as to why we're interested in the toenails. So my graduate student, Kevin Griffin, set out to achieve these 3 different goals. One was to be able to characterize and quantify the amount of heavy metals that we find in firefighter toenail samples. The second goal was to be able to describe differences that are seen in the heavy metal concentration across different firefighter groups. Is it possible that, say, a captain, a lieutenant versus a chief versus a driver operator or a firefighter have different concentrations of metals, which is very possible based on exposure. So we wanted to look at those differences. We also described the association between the job characteristics, like what they're exposed to, and heavy metal concentrations using regression modeling. So which firefighters participated in this HEAT pilot project? So we thankfully had a total of 94 brave firefighter participants from both our Canadian partners and our American partners that attended 2 events. The first event was the Redmond Health and Safety Symposium, with many thanks to the IFF for our opportunity to present and collect data there. We collected 54 samples. And then at the Affiliate Leadership Training Summit, ALTS in Orlando, we collected an additional 40 samples from 40 firefighters. And the recruitment and the collection of this data occurred between August 2019 and January 2020. And we received IRB approval from the University of Miami to be able to do this study. I just want to say that the HEAT study is sort of like a piggyback on the thyroid study. At both of these 2 sites, we were doing a large study looking at thyroid screening. And we asked the firefighters to provide their toenail samples at the time, and 94 brave souls said that they were not grossed out and would be happy to donate their toenails. So what is the inclusion and exclusion criteria to participate in the study? So the eligibility is that you had to have been an active firefighter, at least 18 years of age, and be able to speak and write in English to be able to complete the consent form and the study parameters. The primary outcome measure of this pilot study is that we were looking for the concentration and the presence of 5 unique heavy metals, specifically arsenic, cadmium, cobalt, chromium, and lead. Some of these, as you saw earlier, with direct linkages to cancer outcomes. We're reporting the results of this study using micrograms per gram. So how much micrograms of metal is present for every gram of nail. So how are toenails collected? So we asked study participants to provide us with as much toenails as they can, all 10 toenails while they were there at the study sites. We labeled the nails to be placed in the small envelope and large envelope. So what this means is that we asked the participant if the toenails from the 2 toes could be placed in one envelope, and then the other 8 toenail shavings and clippings could be placed in an envelope that was going to be labeled small toenails. And the reason there is because we can look at differences in concentration between the large toenails, which may have a slower growth, versus the smaller toenails that may have smaller shavings and require bridging them together. These toenails can be stored at room temperature until we go for analysis, which is great because sometimes using some of the other biomarkers like blood, urine, and saliva requires refrigeration and requires a lot more resources to do. So toenails makes it really flexible in terms of how information is collected. So how are these metals analyzed? So briefly, it's a sort of a 2-part way of how you analyze toenails. First, the nails are cleaned prior to analysis. It goes through a sonication procedure. So basically, after you receive the toenails, we got to make sure that we clean them off in order to remove any artifact or debris that may be on the surface of these nails. And the way you do that is you sort of put them in a sonicator. So it's kind of like a drying machine that'll shake them and vibrate them at really high frequencies in order to take off any surface particle that may be on the top or the bottom of the nail. And that's not, analyzed as part of the study. So there goes through a series of washing procedures of rinsing the nails with acetone and deionized water and then dried overnight. When that's done, the samples are weighed so that we know how many grams of the toenails that we have. They're digested in a solution of nitric acid based on the weight of the nitric acid. Then they're further diluted into water in certain amount of concentrations before they're placed into a machine called ICP-MS that uses an ionization technique to look at what type of metal is present and what concentrations. So again, the metals that we assessed was chromium, cobalt, arsenic, cadmium, and lead. So we also asked the firefighters a survey so we can get some additional specific information about who they are, their characteristics, what they do for their job, and what do they do as a firefighter. So we had some main predictor variables, meaning some variables that we wanted to look at the relationship between the heavy metals and these variables. So some of the questions on the survey asked them how many years they were as a firefighter, if they had a second job, because we want to know if their exposures came from something beyond just being a firefighter, what rank are they within the fire service, and what type of schedule they have. We were also able to assess the number of fire runs per month, how many interior and structural fires they participated in the previous timeline, the roles that they perform at the fire scene, and the number of fire calls per month. And also you can see that we collected some variables on social demographic status, including their cancer status, if they've ever been diagnosed by cancer by a healthcare provider. So this is a very busy slide, so bear with me as I try to explain to you sort of high-level statistical analysis. This is for our scientific colleagues that may be interested. So basically, for the survey data, we analyzed categorical variables and frequency variables and continuous variables in this analysis. So continuous variables were assessed as means, and then categorical variables as frequency. So how often do you see that come out? And then our main outcome measure, which is the type of metal and metal concentration, we look at the mean, the standard deviation, the median, the 25th and the 75th percentile, the min and the max for all the values of the metals. Now, one of the things that we saw early on is that the toenail metal concentrations were skewed. So all toenail metal concentration values that were used in a linear regression model had to be log transformed. So what that means is, like, if you plot on the top left the values of the metal concentrations, they seem to be sort of bunched up in a certain area, and this is very common in environmental health data. And so one of the techniques that our biostatistician, thank you, Dr. Rosengal, teaches us is that we have to log transform the data in order to be able to make relationships between the metal concentration and the survey data that's reported. Okay, so now you're curious about what we found. So the results on the demographics. So among the participating firefighters in the HEAT pilot project, the average age was about 42.4 years of age. Almost 95% were male firefighters, 92 identified as Caucasian males, 93 identified as non-Hispanic. Close to 76% had said that they have never smoked in their entire life, and 10% had identified a previous cancer diagnosis. Okay, so here are some of the occupational characteristics of these same firefighters that are participating there. This is just so you get a broad picture of what we see. So on average, the firefighters in this study had been practicing as a firefighter for almost 18 years. The number of days of work per month is about 10, which is consistent with career firefighters, that you work between 9 and 10 days a month. The average number of fire runs per month was about 26 fire runs. And then interior unstructured fires was about 11, and the number of fire calls per month is about 17. All right, and then when we look at the second table on the right, you can appreciate the distribution of the ranks of the firefighter. So you can see almost half of our sample was basic entry-level firefighter paramedics, followed by 8% that self-identified as the driver operator, 20 were lieutenants, 23 were captains, and then we had just 6 or 7% were identified as some type of fire chief. Interestingly enough, 25% of our sample said that they had a second job, and the most frequent type of schedule was a 24 hours on, 48 hours off at 40%. And then the role at the fire scene, the most common type was an interior firefighter, followed by a firefighter that maybe had multiple roles during fire suppression activities. All right, so heavy metal concentration. So I'm going to spend a couple of minutes on here because this is really important to describe and explain what we see here. So overall metal concentrations in the firefighters for the 5 that we were looking at on the machine, chromium, cobalt, arsenic, cadmium, and lead. The first column tells you the average concentration that we found in all samples for all the firefighters in the study. So you can see chromium was at 0.77 micrograms per gram, cobalt was at 0.2, arsenic at 0.1, cadmium was not 0.00, non-detected, and lead was about 0.21. The following 4 columns tells you the standard deviation of the mean, the median, the 25th and the 75th percentile for the entire sample, and then the lowest value that we detected and the highest value we detected. So the highest means among all samples of toenails who had the highest value there. And then we provide a reference level and a published level. And these are based on 2 studies that are related. So the reference level is based on a published study by Cadarella in 2018, where they were looking at toenail elements in Pacific children. You can imagine that it's very difficult to find normative data or reference data for what concentrations one sees in the general population, so that I could tell you whether this is high or low. That not a lot of people, give their toenails and, from the general American population to be able to characterize it. This is a science that's sort of evolving and pioneering. The ideal answer is that we don't see any type of these heavy metal concentrations in your body, but we put them there as a reference value. The second is the published min-max ranges, which is a study by Teslov in 1993, where in the general population, they actually did take measurements of the trace elements in some people for biological monitoring, and they found these values in there. So you have them as a reference to you. So let me take a few minutes to go metal by metal and tell you a little bit of what we saw and we learned within the sample. So I'll draw your attention to the right, where we look at the histogram or the bar charts, where we look at the distribution within the sample. So remember, we had a total of 91. We dropped from 94 to 91 because there was 3 samples of toenails that we were not able to use in our analysis. What you see here is the splitting of those 91 firefighters between those that had a value that was below the reference level, and then those that were above the reference level. So in terms of chromium, you notice that in the firefighters that were participating, almost 62% had an unhealthy level or above the reference value. So they had chromium that was slightly higher than what was that has been documented in other studies. When we look at cobalt, we actually see 26% of the sample, a quarter of them, had elevated levels of cobalt compared to the entire sample. And when we look at arsenic, everybody thankfully was below the reference level. And when we look at cadmium, we see that 1% of the sample just had an unhealthy exposure level. And then the last heavy metal, which is lead, we saw that 2% of the sample had an unhealthy level of lead present in those toenails. So now we want to start taking a look at relationships between what the firefighter reports and what the concentration of those heavy metals at. I'm going to highlight for you the items that we found to be statistically significant or numerically values that came off. So we saw a relationship between the concentration of chromium and the age of a person. So as the age of the firefighter went up, the level of chromium went down. So that could be a function due to age, or it could be something due to exposure. We also see a relationship between smoking status and cobalt exposure. So comparing individuals that were former smokers, they had sort of different levels of cobalt exposure in their toenails. And then we also saw a relationship between cancer status and cadmium. So that individuals that had confirmed that they did have a cancer status had a slightly elevated level of cadmium exposure. So now let's take a look at other characteristics of the firefighter that were positive. I'll bring your eye towards the row that's called current rank. So we're going to compare these individual ranks to the basic rank of being a firefighter. And we saw that individuals that were in the role of a captain had slightly elevated levels of cobalt. And then similarly, when we look at the role of the fire scene, firefighters that had multiple roles during the fire scene had elevated levels of chromium. When we look at logistic regression models, and now these are models that describe the probability of reporting, in this particular case, chromium above the threshold, we noticed a couple of things that stood out. So now what we're saying is, how likely are you to report it? So age was actually a protective factor for having high concentrations of chromium within the toenails. So you can see that it was protected because it's less than 1. We're over here where it says age 0.93 less than 1. We also noticed that individuals that self-identified as Hispanic or Latino were also had tended to have significantly lower concentrations of chromium compared to their non-Hispanic, non-Latino firefighter counterparts. We noticed that lieutenants were also less likely to report high concentrations of chromium in the blood. And then in terms of shift schedule, we noticed that firefighters that are on the 24-48-hour shift compared to those that do a 24 to 72-hour shift were 4 times as likely to have a higher concentration of chromium compared to those that were 24-72. So this is a very interesting finding because the organization of the shift work may potentially play a role in the concentration and elimination of heavy metals. Let's take a look at cobalt for a second. There was 2 findings that came out here to be statistically significant. So in terms of rank, we see that captains were 3.3 times more likely to have higher concentrations of cobalt above the threshold compared to those that didn't, that were in the regular firefighter line. And then similarly, in terms of the role at the fire scene, those firefighters that reported multiple roles tended to have a higher concentration of the heavy metal cobalt compared to those that were in interior firefighting roles. Okay, so univariate logistic regression models for other metals. What we found here is that there is sort of a likelihood of unhealthy exposure. We only performed it for chromium and cobalt in this preliminary analysis in order, because some of those came up significant during descriptive statistics. And also the univariate logistic regression for the likelihood of unhealthy exposure couldn't really be performed for arsenic, cadmium, and lead because there was not enough participants in the unhealthy exposure group for the comparison. As you guys remember the charts, some of them had, the histograms had sort of lower ends. So this is really an important point about having firefighters participate in research because we do need more individuals to make better statistics of what we see in terms of concentrations. So in conclusion, the result of the study has shown us that chromium had the highest average concentration while cadmium had the lowest average concentration compared to the other metals. So if you had to sort of rank order them, you see that chromium was greater than lead, greater than cobalt, greater than arsenic, greater than cadmium. And among those firefighters that participated in the study, we saw that almost 63% had some unhealthy exposure or were above the threshold level for chromium. And about 27% had an unhealthy exposure or above the threshold level for cobalt, which is different for those that had arsenic, cadmium, and lead. And lastly, heavy metal concentration is related to the role performed at the fire scene. So you can tell that from the last two individual models that the organization of the shift work, as well as the role that's played on the fire scene, seems to be related to the heavy metal concentration that we saw in the toenails. So what are the limitations of this study? Because it's definitely not perfect. So remember that the survey self-report, we don't have any objective reports from the fire scene showing the exact amount of time that somebody was in a fire scene. Rather, this was all just self-reported from the firefighter. We also had a very relatively small size of firefighter participants. There was only 94, of which 91 samples were used because 3 toenail samples were not good, which again highlights the important and urgent need to have more firefighters participate in these type of biological samples. We also didn't account for any dietary sources of exposure. So you remember at the beginning, I showed you the different point sources of heavy metal. So individuals that say like have high consumption of fish may have a disproportionate exposure to say heavy metals like mercury, like inorganic and metallic mercury concentrations that are found in the food supply. And so it's really important when you do heavy metal studies to assess dietary intake that may potentially influence the concentrations that we see in circulation, not just that from the exposure at work. We also didn't account for geographic differences. So as I mentioned earlier, houses are all built differently, with different structures. Like a house here in South Florida is not the same as our building and multifamily homes in the Northeast. And so those materials, as they burn, will theoretically have different presence of metals and concentration of those metals, which could be account for geographic differences. Although we did have firefighters that participated from both Canada and from the United States. Remember that this was a cross-sectional study design, meaning we only took toenails at one point in time. We haven't done repeated toenails over time to see if those concentrations change, or if this is just a fluke and we saw this in one sitting from one picture. And then the majority of the participants were in some type of leadership position and may not have had too many active scene. We saw that 40% were mainline entry firefighters, but there was people that were in lieutenant and captain roles, so they may not have direct necessary fire exposure during fire suppression activities. But the study has some really awesome strengths. So being able to use these toenails as a non-invasive way as a biomarker for heavy metals is really cool, because now we can document over time whether or not these heavy metal concentrations are present or absent and to what degree. Here in Florida, our firefighters have raised to us the concern that if they do unfortunately get cancer, they're required to present evidence that they were exposed to things that are carcinogenic. And being able to provide heavy metal concentrations in the toenail is one very simple, non-invasive way that could be collected through the postal mail or in person to be able to characterize those heavy metal concentrations over time. It's also really easy to store them. It doesn't require a lot of space, and they can be held at room temperature as long as there's not a lot of humidity, which you place desiccants inside the envelope in order to preserve and keep them over time. The majority of the firefighters really approved the idea of collecting the firefighters, of collecting the toenails. They found it as an acceptable and easy way to be able to donate and participate. The other really neat strength was the tool that we used. We used a validated technology, ICP-MS, which is very accurate in detecting these heavy metals. And there's a lot of really neat ways of doing metal analysis. I wanted to point out that from these pictures, if you see, this is sort of like a laser focused in on a sample. When you use ICP-MS, once you've already taken your toenails and you have them as a powder form in liquid suspension, the laser points at the solution and tries to identify which metals are there and at which concentrations. So in this study, we actually pulverized all the toenails and made them into one individual samples. But there's other analysis approach where you can actually shoot a laser at the full toenail, clipping, and then try to identify along the depth of the toenail where that metal is deposited. Almost like rings of a tree. If you've ever cut a tree and you see the bark, you can see that there's different rings on there, which are the lives of the tree, how old it is. And so you can actually point a laser at the toenail and see if the heavy metal concentration is greater at the distal end or at the proximal end to get a better picture of the metal concentration. And also this study, one of the really neat strengths is it's the first time that we've been able to look at internal absorptions of heavy metals in firefighters, to be able to characterize it beyond what we would do, say, in clinic, of doing a blood draw or a urine sample to get an immediate point source of heavy metal. There are some important public health messaging here that I want to share with you all. So the results of this study suggest that there is the presence of heavy metals in firefighters through the use of these toenails as biomarkers. We have a strong need to be able to repeat this experiment with repeated measures, collecting multiple toenails on the same firefighter over time in order to see how heavy metal concentrations fluctuate based on the type of exposures that they go to, i.e. the number of fires and the type of fires that they go to. This study should, when it is repeated, should be done with the collection of other biomarkers, such as blood or urine, in order to validate acute and long-term exposures. So what you see in heavy metals shows up with what you see in urine and saliva and blood. And then lastly, toenails as a biomarker of heavy metal exposure is a really effective way to do biomonitoring, right? So it's very easy just to ask firefighters to cut their toenails. We can save them, and if we needed to characterize it, we could take a look at it and then relate it to health risks as we go on. So that's the end of the presentation. I want to acknowledge the efforts of my graduate student, Kevin Griffin, who over the last 2 years dedicated his time to collecting toenails, the toenail guy, as part of this project. Our Firefighter Cancer Initiative team is indebted to the International Association of Firefighters, Vice President Patrick Morrison, and other staff from the IFF who helped us coordinate these studies at firefighter events to collect that data. I am personally indebted to Dr. Tulay Koro-Singal and Dr. Shanta Dar for mentoring Kevin during this process, and to his lab partners and other members of the FCI team who supported Kevin in making the HEAT pilot study possible. So thankfully we have 15 minutes. All right, so we finished in good time. So I will entertain any questions from the audience about this study, or try to confuse you some more.
Oh, you were? Go ahead. Hi, Alberto. Quick question. Why don't you guys test mercury as well?
Okay, so the question is about, so hey, Emery, the question is about mercury testing. And the reason is because the detector on the ICP-MS, I think, was only useful for those 5 metals that we did in the study. I understand that it could be expanded to other metals, but forgive me, that's not my area of expertise, so I'd have to defer to Dr. Dar for future analysis.
Okay, thanks.
Alberto, I believe I can help out. I think that it's because of the boiling point of mercury. It's much lower than the other metals.
Oh, okay. Thank you, Jeremy.
You're welcome.
Are there any other, it's great to see some familiar face or at least names on here, so thank you all for coming. Are there any other questions I can answer about the project? All right, well, thank you to all of you for joining us this afternoon, and thank you to our firefighter partners that were able to make it. This presentation, if you need to watch it again because I confused the crap out of you, will be available on the Firefighter Cancer Initiative website. On behalf of our FCI team, thank you for joining, and we'll see you next month with a new topic to present you. Take care, everyone.